I will try to get out of the way as much as I can on my stream. I mean, but otherwise, I think we can continue with our little session. We now have MrDiver giving a presentation on. If I were prepared, I would have the thing somewhere.
It's fine.
The verts and frags of OpenGL. Now I have it here. Thank you very much for agreeing to give the talk, and yeah, looking forward to hear more things about OpenGL. Stage is yours.
Okay. Then, yeah, well, welcome to my beautiful talk about OpenGL. You probably never heard of it before when looking into Manim because it is not really obvious why it is there. But I will show you quickly why it is interesting to have OpenGL in Manim, and then we continue with the talk. The first thing that we need to figure out is what is the difference between what we normally use with Manim and like OpenGL, right? Because the normal or default renderer in Manim that we saw in Jason's talk before is Cairo, and it is just the CPU renderer which does stuff on the CPU and renders to a picture, and then that's it, right? But with OpenGL, we have a whole new world of things we can do because we get the ability to have an interactive presentation. And this makes it really fun to work with Manim because we can just make our animations do the things we want to do, but we can decide live while talking when they should happen, right? So that's the first primer. Why do we want OpenGL? We want it because it's interactive and it can make our animations interactive, and also it's a lot faster. So then let's get into it. How does OpenGL work? Or what is OpenGL? Many people will probably think, OpenGL, it's a library. Like, okay, can we use it? But that's not quite true. OpenGL is not really a library that we can use. OpenGL is just a standard by the Kronos. Is it an institution? I don't know. But by Kronos, they set up a standard for interacting with a graphics card, right? So they said like, okay, we want to have the ability to draw triangles and like draw lines and points and all that good stuff, right? And what we are using when we are talking about using OpenGL is basically the implementation of the standard in our GPU driver, right? So we are never really having a library that is OpenGL because that doesn't exist, but we have a driver which implements OpenGL, most likely our NVIDIA driver or AMD graphics card driver. And then we have a library around that which just simplifies using the driver commands, right? So in most cases, we don't need to worry about that, especially in the case of Manim because we are using Python, so everything is abstracted away. And before I go further from here, I will just say everything that I say in this talk should be probably verified by yourself if you want to learn about OpenGL. Just go to learnopengl.com. Yes, this is kind of an ad for a website which you can just visit, but just visit that page. This has everything that you will ever need to know about OpenGL, and then you will be happy, right? And for the second information, we are using ModernGL as a library to interact with the OpenGL driver implementation in Manim. So back to the talk, right? So how does this work, right? So how does OpenGL work under the hood? It is really interesting because it's quite different to the concept for Cairo. Because in Cairo, you could just say like, yeah, draw this line, and the CPU figures out how or where to put the pixels. In OpenGL, it's a little bit different. First, we need to think about what we want to draw, right? So if we want to draw a triangle, we just need to imagine like, okay, we need a triangle. Like, what does it? What is it made of, right? So the first thing is probably vertices. Our triangle is made of vertices, which are just points in some space. And this is basically true for every shape we ever want to draw with OpenGL. They are in 3D space, just points scattered around, and they define how our shape looks. There are different versions of that, but like we could use different shapes basically instead of a triangle, but the basic shape we are using in OpenGL is right. And when we have our vertices defined for a shape, then we can do something funny with it because we can put them into basically an OpenGL shader. The first part that OpenGL uses is the vertex shader, which basically takes our points and just transforms them around in the space we define. Right, so we can just move the points to somewhere else where we would like them to be. For example, if we want to have a camera, which basically moves our whole shape around, we can just move the points in the vertex shader and they will be transformed accordingly, right? So if we have our vertex shader, which takes every point in as like a single object, kind of, we can just move it to the left or right or whatever we want to do, right? After we did that, and we will go into examples which are way more complicated than this later, we can do something funny because now that we defined how our shape should look like in the vertex shader, or where it should actually be in some space. There are many spaces in OpenGL, but I just say some space. It's a little bit simpler for the beginning. Then we need to build our shape, right? So we need to connect our funny vertices with some lines, which is basically the shape assembly, and it assembles our vertices into primitives. As I said before, OpenGL by default uses or not by default, you have to specify it, but for the most part, we just use triangles as our primitive. So any number of vertices we put in, probably a multiple of 3, it will be assembled into triangles, and that will make up our shape. After we did that, or after OpenGL did that, kindly for us, and assembled our shape on the GPU, we have the ability to add some more geometry. In most of the cases, we don't want to do that, but there are some cases in which we actually need to dynamically add geometry to our already existing shape, but we will skip that for now. Yeah, and at the end, we actually need to do something with our shape that we now defined, right? And most likely we want to color it and display it to the screen, right? And in OpenGL, there's something called a fragment shader for that. This is basically the last part of the render pipeline. And in this one, OpenGL just takes in our vertices that we defined before, and puts some color into them. There are some steps in between, but I think they are way too in depth to go over right now. So, what happens in the fragment shader? The fragment shader is a little bit of magic, kind of, because it just takes a position in our shader, kind of, or it doesn't need to take a position, but it can take anything that we want it to, defined by the vertices of our shape. So we can just attach some attributes basically to our vertices, and the fragment shader will just take them in. But there's a twist to it because it interpolates by position. So if we expand our example from before with the triangle to like a quad, then we can basically just attach colors to all the vertices, like the 4 in the corners. For example, black, green, red, and yellow. And the vertex shader will make sure that if you have like many pixels in between for your shape, that it's just interpolated. How that works, I am not quite sure. It's really interesting magic that OpenGL does to interpolate stuff, but it is super fast, and we will see an example later. But yeah, on the left side, we can see an example of like a fragment shader. We basically define the version of OpenGL that we want to use. Then we have like input attributes, output attributes, and in the bottom we basically have our main function which does the actual calculation. In this case, we just take the interpolated color that we attach to the vertex and then put it back as an output color, which results in this kind of shape here, where we just have some colors if we have the corresponding colors attached to the vertex, right? But it is really hard to show how OpenGL works without actually showing how OpenGL works, because the theory is easy, the practice, the practical thing is hard. So we actually need to go into an example, which we will do now. And I prepared some funny example here. Right? So we have to think about what we want to draw, right? So the first, I hope the code is visible. I think the code is visible. Yeah, but the first thing we need to think about is like our vertices, right? So we will just define them in a list of lists and have like 4-dimensional points. Don't ask why they are 4-dimensional. It works. It is basically later for transformations with a matrix, but just you can do it in whatever way you want, basically. But we will just make a list of vertices. In this case, we will have a point at -1, -1, 0, 1, -1, 0, 0, 1, and 0. So 3 points. It is oddly specific that we have 3 points because those are our 3 points for a triangle. And the second thing we can do is basically have a list of colors. In this case, the same thing, and they will match up in length with our like vertices. So we can basically attach colors to our vertices. And you have to imagine in Python it's a little bit weird because most of the low-level OpenGL stuff is done in C and C++. So a lot of stuff is abstracted here. But they will just be matched up one after another, right? So we will have like a color and then, or no, a vertex, and then we will have the color right after it, and then again the vertex, and then the color after it, just to think about how it looks in memory. Right. And in general, we will just tell OpenGL, hey, that is the thing, or like the general shape of the data that we want to have, right? So we just say like, yeah, we want 3 vertices that we have, and we actually tell it just like, oh yeah, it's float 32, or like a floating point number with 32 bits. It has 4 values, or like, yeah, we want 4 of them, or a vector of 4, and we just have that 2 times for the vertex and the color. So we actually can put that into the shader later. So talking about the shader, we need to figure out how this stuff gets into, yeah, being displayed on the screen. For this, we have this sadly interesting formatted string, but it is fine. I think everyone can read that. This is our first shader in the pipeline that we talked about before. This is the vertex shader. With this one, we can move the points that we defined here into some different space that we want. So what happens here is we define the 2 attributes that we set down here with the same name. They have to be the same name because it's like statically linked in the end with the shader. And then we just get those as usable values in the shader, and it will just loop through them in parallel. Yeah, and then we can specify any number of output things that we want. We can name them however we want. It doesn't really matter as long as we specify the out keyword before it. Then we have some funny things here, which you can happily learn about on learnopengl.com, which are like projection matrices and like Froster matrices and all that good stuff. I will not go into that in any way in this talk because it's really difficult and like uses a lot of math. to explain how everything works, but basically it takes your points and transforms them into like a 3D space which has perspective. But you don't need to do that in OpenGL. You can just leave it out, but in order for it to render in Manim right now, we just need to use that. And then we basically take our color from the input that we specified, we put it directly into the output that we want, and then we see this GL position thing here. This is kind of a macro or like a predefined output variable. And we just tell OpenGL with that, yeah, the current vertex you are like looking at, it should be placed in this position, right? And we have some calculations in between with the matrix, but we could basically delete everything of that part and just put the vertex in here if you really wanted to, and it would still work. I could actually do that right now, but I will do it after I show the full example. Right, and then after this one is defined, after the vertex shader is defined, basically everything for the first part of the pipeline is done. After that, OpenGL will go ahead and build the shape and go through the geometry shader if we have any. In this case, we don't. And then we'll just walk through the pipeline until we arrive at the fragment shader. This is the second part we have defined here. And this is a pretty simple shader because it just takes the vColor attribute that we defined before. So it's exactly the same name as in the vertex shader. So they are linked to each other. And we just take the color as input and output a fragment color. In this case, we can actually do whatever we want with this, but I think somewhere we need to have defined like which one is the actual output color. Which in Python is still a little bit weird because we are using many layers of abstraction, but we just take this one as our output color right now. Right, and then the main function in the fragment shader is basically just, yeah, put the color into the actual color that is displayed on the screen, and the rest will be done in by OpenGL and our graphics card. Right, so if we have done that, then the rest becomes really simple. We just need to tell OpenGL, hey, I mean, we have a lot of abstraction around it, but we basically just tell OpenGL like, hey, this is our data. We want it to be rendered with the shader we wrote here, and then we are good to go. And if we run this example, then we will get a funny little triangle, which hopefully stays open in the window. Please don't close on me after 5 seconds. You are closing on me. I knew it. Let's do the interactive embed fun. And then we will have our triangle defined as we wanted it to be, right? So we have like 3 points, and basically the colors we have down here are the same colors we have here on the triangle. And this is basically the first thing you always do when you are learning OpenGL, just rendering a triangle. As I said, learnopengl.com, the perfect resource for that. Even if you are just following along with Python and modern GL, it makes sense with the terminology they use there. So you can probably follow along and do that in Python too, if you really wanted to. Yes, but now we have a shape and everything works fine, right? And if we now go ahead and delete everything from here, or no, we don't need to delete. We just take the in vertex from before in the vertex shader. So we don't move anything. We just pass it through to the next shader, basically. Then our triangle will look like this. Which makes sense because now we just deleted every transformation, and the space OpenGL normally uses only goes from -1 to 1. So our points that we defined here with -1 and 0 and 1 and -1, they are translated to like the window size. And if we resize that, it should, oh no, because we don't resize the buffer, right? We forget about that because we haven't have that implemented right now, but in any way, it basically just doesn't scale to anything. It just uses the whole window, right? And that's why we need the magic here with the matrices, so we can actually have like a useful shape that we can move around. Because we don't want to have everything in the space of -1 to 1. We want to have useful coordinates. In this case, the Manim camera coordinates, right? But yeah, I guess that's everything for that part. And you can experiment around with it in Manim, basically just like making some meshes. I think we have documentation on that. If not, we have the OpenGL.py in the examples folder, and everything is explained there. But to go a little bit deeper on how Manim actually uses OpenGL, because that was just a simple example, I will, on one hand, forward you to a paper, but on the other hand, I will also show you how that works. Probably in a live example, which is not a good idea, but Manim, as we heard before, uses Bezier curves to basically render everything. And in OpenGL, we cannot just be like, yeah, draw this curve and the CPU figures everything out. In OpenGL, we need to think about the shape we want to render, right? And a curve is not a triangle. I think we all agree on that a curve is not a triangle. So we need to figure out how to render a curve with triangles. And some smart people at Microsoft basically broke their heads and hit their heads against the wall to figure this out. And they figured it out. There is a really funny formula right here. It looks so simple, but it is really amazing. Which basically gives us the ability to render any quadratic Bezier curve with any number of triangles. And they go into a lot of detail on how this works. But basically, that is what Manim does. And how this works, I can show you right now, basically. So what we need to do is basically attach, or let's first do the funny shape with the triangle, that we can do this correctly. But basically, it uses. Does it work? It is inverted. That is great. Why is it inverted? Let's do that. Or no, just -1. Right? But basically it uses or exploits math in the shader, right? So we want to have a specific function rendered for every pixel, which is in this case this weird quadratic formula. But it uses the ability to basically interpolate any value we put or attach to our vertices. Yeah. It exploits the ability that we can basically attach an attribute to our vertices, and then it will magically interpolate it, and we can use it in the fragment shader. Right? So if we look at our still inverted triangle, why is it still inverted? I'm so confused. Do we have the coordinates flipped in Manim? It is really funny. Can you display that one? Is it broken? No, now it works. Okay, right. So we have this one. And then we will just exploit the color right now because I'm a little bit lazy, but we can put in those funny values here, like 0, 0, 1/2, and 0, and 1, 1. So 0, 0, 0.5, and 0, and 1, 1, I think was the right one. Yes. Right. If we save this and render this, it will look really weird. But now we can go into our fragment shader, which basically is the function which determines what the color is, right? And now we just do an if-else statement. And in this case, we want, what was it? We want the first value squared. So we take the v color times itself, or like the first value of v color, and then we tracked it with the second value. And you can access the values basically by typing .x, .y, .z after the actual vector. So OpenGL has a lot of pretty cool features to interact with vectors. But there's enough documentation in the world for that, right? But basically, what we want now is this here, this funny sentence which says if, and then it should be less than 0. And we will just do that in our fragment shader. So we will tell OpenGL, yeah, if that's less than 0, then we will actually put a color in. In this case, we will just make a new one and make it red so that it's like exactly as in the paper. And else we will discard the pixel, right? And now if we save it, then hopefully it does something. No, it doesn't. Life experiments, isn't it great? Probably, what did I do wrong? Let's debug it. Probably coding in a string is not the best thing that you can do. But it works somehow, right? So if we go back to the color, then it displays something, right? Do I have the chat? Oh, did any messages pop up in the chat? Oh yeah, yeah. That is a good hint. I forgot about that again. Thank you very much. I always do that when I am writing in OpenGL. So what the first or the notice was is that the last value here is the alpha value. And it needs to be 1 as nothing will be visible. But now we have a funny curve here, right? And it looks exactly like in the paper. So yeah, that's how Manim uses OpenGL under the hood, basically. And we can verify that by going into the funny shader here. And it basically does the same stuff with different letters, but we have the same thing here to render like the curves. Right, and there is a lot more stuff you can do with it, obviously, because you basically have like an infinite amount of code that you can write in the fragment shader. So yeah, infinite possibilities, but that's how we use it. But now, what's or let's go on to the next point of the talk, which is basically how if someone now wants to actually go and dive deep into OpenGL with Manim and like work on the renderer and like fix bugs with OpenGL, like what do people need to know, or what is the tool set we use in that case to actually work with OpenGL and debug it? And in this case, we use a funny little program called RenderDoc. So yeah, you can probably not read the name of the program, but yeah, RenderDoc, we will probably have it somewhere up later. And this one is a funny open source tool which lets you debug any kind of shader programs or like anything that happens with the GPU, right? Which is really useful in our case for rendering like with Manim, because we have a really complex system for rendering with all the meshes and all the things we are calling in between. So sometimes it's really good to just get a sanity check with an actual tool that is designed for debugging it. And how do we use this? You can probably not read anything on my screen, but it is fine. You will see the good stuff, I suppose. But the first thing we need to use, or we need to do after we installed it, is probably closing the presentation. And we need to figure out, like, if you have downloaded the repository, you will by now know what poetry is. And we need to get like the path to the actual Python executable that our environment is using. In this case, it's this funny thing here, the executable, and we can just copy it, and we have the executable path in renderdoc right at the top, and we can just paste it there. The working directory should probably be the folder in which you normally run your Manim commands. So you can, if you are on Linux or like the Windows subsystem for Linux, you can just type pwd, which basically just gives you the path to your current working directory, and you can just paste it in the working directory part, and then after that you just put in the normal things you would call Python with in order to render with Manim, right? So we do -m, Manim, -p, then example scenes. In this case, I have the presentation .py for my talk. And then I have like --renderer equals OpenGL. And then I have force window. So it actually kind of works because sometimes it bugs out. And then a quality specifier, which we really don't need, but I do it anyway, right? And basically that's it for the basic part. And now if we click on run, it should pop up a window, which actually has our little Manim animation. And basically that's it for the first part. We can close the window again. Right. And now we have a full capture of what happened in, basically in Manim and how it rendered all this stuff, right? On the left side, in this case, we have like the full timeline of events that happened. So we started with initiating a frame, then we did a capture of what is inside the frame right now, and then we have like a color pass, which is basically in our case just the the triangle, right? Because we don't have anything else laying around. And we can look at many different things for that. For example, the first thing I really like to use when using RenderDoc is the mesh viewer, because the mesh viewer gives us the ability to inspect every single vertex that we put into our shader, right? So it is really useful to inspect like, hey, what actually happens in the shader, or like which data does it get? Because sometimes when you are like working in the renderer and you mess up something and it just doesn't render anymore at some point, maybe there's still some data sent to the shader, and you can look at it like this, and then you can figure out, oh yeah, I messed up the triangulation, or like I shifted them into infinity, or like everything is 0, and then you can figure out from there what's wrong, right? Or if you want to debug your actual shader, then you can also use it. Because you can basically just look at like what comes into the shader and like what goes out, right? For example, in this case, we see this little blue square here around it. This is the coordinate space for OpenGL with the -1 to 1 ratio, and then the output is actually like the whole screen with like the transformed triangle, right? And this goes basically also for the fragment shader, which is a little bit more interesting, I suppose. And for this case, we can go into the pipeline or the pipeline state viewer, basically, on our specified frame that we want to debug, right? So in this case, we just want to see what the triangle called it. And then we can go into the pipeline thing, click on the fragment shader, and then there's a little small edit button. And then we can basically view like the fragment shader and what it did. And because sometimes it's really annoying to just recompile and like always render the same scene with Manim, right? We don't want to do that. We can just edit the shader directly in RenderDoc. So if we now look at like our output, it has like a red curve that we have. And if we go into the shader and just like make it blue or something, or yeah, let's just change the color, right? Then we can click apply changes on the top, and then everything is rerun over the capture. And then if we go into the texture view again, it actually changed the output, right? So if we want to go ahead and now debug, for example, the other case, like the inverse case of this paper, and figure out how that works, but don't want to rerun the scene all the time, then we can just go here, like change the sign or like the comparison, and then we click apply changes. Does it work? Oh, I have to reset, I think, before, or does it work? No? Where's the button disappeared? Where's the menu bar? Why is it like this? Okay, don't do that to me, please. And I think now we should be able to change this. Click apply changes. Right. Okay. I don't know why it doesn't want to go back into the thing anymore, but it's fine. And now it reset it. I love it. Yeah, sometimes technology is great. Let's click on editing. Change the comparison, click apply changes, go back into the viewer, and now we have the other case, right? I don't know what I clicked in between, but something funny happened. But now we can look at like the output of that, and it makes it really easy to like write new shaders and like debug what is broken in the shader and everything. And if we go to a more complex scene, basically, for example, my circle scene, and we debug that one, then it should open the window again. It should draw some stuff here. And then we can basically take a look again at the different things that OpenGL did. So first we did a clear for the background, then we drew a circle, then a square, then like some text, and after that, I don't know what the last call did, but it did something with 3 verses. But then we can verify like, okay, is the text actually like rendered correctly, right? So we can look at like what is the input data for the shader, like does it look correct? In this case, it looks really weird, but text just looks like this if it's triangulated, right? And then we can look on the output, like is it transformed correctly? Or we can just like play around with the shader or look at the output of the geometry shader or something like that, right? So we can basically go through every single step that OpenGL does and figure out what is going wrong if we need to. And again, you can just go into the fragment shader thing and or like the vertex shader thing, click on the edit button, and then like move everything around, right? Or the vertex shader, yeah, it does have an edit button, right? So we can just basically move everything around how we want it to. For example, we can change y and x, which is a really weird idea, but if we... Oh, it doesn't change anything. Right, okay. I should test the stuff before I do it. Probably because... Oh, it's just the normal. Right, so... And if we do it like that, then everything is like flipped to the right and inverted, right? So we change the axis and then, yeah, you can debug stuff like that. And that makes it really easy to have like a good interface for debugging shaders and debugging OpenGL and how everything works. And it makes it a lot simpler than just restarting everything over and over again, right? And basically that's it. There are some other funny things where you can just highlight the different things so you are actually sure about what it does. In this case, you can see like the mesh for the circle. Like if you draw it like this, then you see like different triangles that are generated and all that good stuff, right? Or for the square, you can see like the boundary and how everything works basically. Yeah, and there's some other fun stuff that you will probably learn about if you really go in depth into OpenGL and how everything works. But I think for like a good entry point, that's enough to know to work with it in Manim, right? So to recap it a little bit, basically how Manim uses OpenGL is we are generating some fancy shape and list of triangles or vertices that we put into our shader. We attach a color to every single vertex in our shader. Or like before that, but we put it together into the shader. And then the shader transforms it into our Manim space or Manim position space, basically, that we defined with all the good stuff that you know. And then it goes on to the fragment shader, interpolates every single thing that you attach to your vertex, and then it runs a function, which is basically your shader, which determines the color, which does some magic in order to render shapes like this, or like fill them out with curves and all that good stuff, right? And in the end, you get a pretty picture that you can look at and be proud of because you animated something. But yeah, that's basically everything about OpenGL in a really, really huge nutshell, which probably cracks around the border right now because there was a lot, or like a huge curve from going from a little animation to the actual OpenGL part. So I hope everyone could follow at least a little bit, but if anyone has questions, and also later on in the future, if you want to work on the OpenGL renderer and like how everything works, then I will be open for any questions that you might have. But yeah, that's it. That's basically the end of the talk. The words and frags of OpenGL. I hope you all know by now what the title actually means.
Well, clap, clap, clap. Thank you very much for this very, very nice introduction to OpenGL. It was very interesting to hear more stuff, or to hear a proper introduction and not always being thrown into just the shader files that lie around somewhere. I have one message. You probably have seen this before because I think we have talked about this before. I just posted in the chat. Have you seen this example before?
Let me look at it. What happens in here? Manim CE OpenGL displaying a cyber. Oh yeah. You showed me it on your stream. That is really funny. I think
I have no idea whether
now,
it still works, but
should I test it?
yeah, you could. Maybe that's interesting for people still listening.
But is it? No, it's community edition, right? So
yeah, it's community. It's community. Naveen at some point worked on this. I'm pretty sure. This also, while you paste it into the file and run it, gives people the opportunity, if there are any questions to the OpenGL talk, then feel free. I'm watching my stream chat and the two locations that I said that people can post questions. If there's anything anywhere, I'll make you aware of it at least, so you can still work with the renderer.
Let's see. Does it still work? Oh, scene. Oh, something. Oh no, I did not save. That is a good thing to do before you run Manim. Always remember to save. Text wrap is not. Oh yeah, because I did not import that. Do I have that? Oh yeah, it still works. Yeah. So this is one of the funny things that you can do with OpenGL, I suppose, if you really spend some time with shaders and figuring out how everything works. I think it should only take in one point, right? It doesn't have a mesh, if I'm not mistaken. Does it?
I have no idea. I
How
have
does
no
it
idea about
render
the details.
anything? Wait. We can figure it out live, right? No. Render content. Yeah, this is like all shader. So basically what we do, actually now that we have the full talk going, right? And we know how to debug OpenGL, we can just do it.
Oh, that's
right?
funny, yes. I want to see what RenderDoc says
just...
about this.
That probably a lot. But I think everything is written in the geometry shader, basically. So the only thing that is put into, or no, the fragment shader, right? But anything that is put into like the shader is basically just a rectangle for the screen. I cannot close it anymore. Now it works. Okay. Oh, that's a huge scene. That was a big lag spike. So yeah, the funny thing is, if we go into like the mesh viewer, there will probably be nothing. Yeah, exactly. That is the whole scene, right? So there's a lot of black magic going on because we just get the rectangle for the screen, which is put into the shader. And if we go to output, then it basically just scales it up to full screen, right? That's why we actually have it in full screen right here. The geometry shader apparently does nothing, which is that makes it way worse. Yeah, and then basically what we have is just the fragment shader left, right? So we go into a pipeline and a fragment shader and click on view. And yeah, it is using signed distance fields, which basically defines shapes through functions, which we could also do in like a example, I suppose. It is using the same principle with the curve here, right? That we can just define a function on based on some attributes with that we attach to the vertices. In this case, we just attach a position on the screen. So we just attach 0, 0 on one end and 1, 1 on the other end with the like rectangle that we put in. We can probably see it with, does it have any attributes? No, it just uses the position, right? So we just use the pixel position on the screen basically. And we have
And I
this
think enter
huge
time is passed
function.
in, right?
Huh? Yeah,
Time is
and the
also
time is
passed in.
passed in as uniform in the top. Yeah, yeah. We just passed the time in as a like uniform variable. Ah, right. I didn't go over uniforms. Right. So a uniform is basically a variable that doesn't go through the whole shader pipeline and is applied for everything that is rendered with that specific shader, and you can set it like anywhere you want at any time. It doesn't have a fixed like time frame where you can set it. So yeah, you can use it for stuff like time where you dynamically want to change like how your shader behaves, right? So it renders different time steps basically. So somewhere in the code, there should be. Oh yeah, that's probably why there's a loop or it updates. Yeah, that's why we have the updater rate. You can't see anything, right? But that is why we have the updater here. So we do add updater, like a time-based updater where we get the scene time, and we basically call set uniform over and over again, which dynamically just resets the variable to a new value in the shader, and OpenGL will just accept it and use it for the funny Cybertruck. Right. But otherwise, this shader in in the end, it is really simple what it does. Because there is assigned distance field shapes. Now, there is a cool website. I am not sure if I can find it again. But in the end, what it does, it just takes the same approach with we take in the 3-dimensional position and we define a function which defines a shape, and we do like a little if statement, and if it's inside the function or like inside a specific boundary, we will like display it, and else we will just discard it. And if you combine a huge amount of these functions, which is done here, where we have like do we have? Yeah, we have like a sand distance field for a cylinder, a sand distance field for a box, a line, or no, that's just a line distance. We have some noise, right? But yeah, basically it's just built out of boxes and cylinders defined in a shader. So we have like some really interesting functions, which are basically the mathematical definitions for the shape, right? And we can use them to define this really cool Cybertruck. right? So we probably have like cylinders for the wheels and stuff and put noise on that. And yeah, in the end, it's for that one, it's a lot of black magic, I would say. But in a normal case, there are some simpler ways to use sign distance field. But that's a good note. There's a funny
Shader
toy,
toy, yeah.
yeah, a funny website called Shader Toy, where you can just look up anything that you will ever want to look up with like OpenGL shaders. Everything here is done in a fragment shader, so everything you see is done basically without geometry, right? So stuff like this, which is the same approach with the Cybertruck, basically defines different functions for different mathematical shapes. So in this case, we have like the sphere, right? And then makes some really interesting math, which basically determines like, okay, we are at this pixel, which color should the pixel actually be, with like taking into account everything that we defined with the mathematical shapes, right? Yeah, so it's probably a whole another world with like making shapes with signed distance fields, but yeah, I I I mean we kind of use it for the curves, right? So the curves are rendered with the signed distance fields for the curve, but in most cases, if you want to use OpenGL, you don't need to do everything in the fragment shader. It's horribly slow, but it works.
Yeah, that's
So
sort
yeah.
of a motto of Manim in some sense. We do lots of things that are extremely slow or inefficient, but most of the time things still work. All right.
Yeah.
Thank you again for this very nice talk.